Okay, I thought I would just give a quick update on recent work appearing since the SROC was published in 2019 on sea level rise. Okay, so first quick message. This is my colleague, Andrea Dutton. She's standing on coral reefs. There are about 8 meters above modern sea level. One is in the Indian Ocean, one is in the Florida Keys. The geologists are telling us that when the world was roughly about the same temperature as it is today, sea level was many meters higher. And that is telling us it's a clear indicator that the big ice sheets are sensitive to a little bit of warming. The current perspective on sea level rise, rising at roughly 3.6 millimeters per year, it's accelerating. The rate is going up. 3.6 millimeters per year is about 2.5 times faster than the average rate of sea level rise over the 20th century. What's changed is an increasing contribution of land ice. In the 20th century, thermal expansion, the oceans gaining heat, getting warmer, was the primary driver. Now land ice has become, the contribution of melting land ice has become the primary driver. That is important, and it should be worrisome because there's so much potential sea level rise locked up in the Greenland and Antarctic ice sheets. This, as of 2019, was the assessment of the IPCC. This is from the SROC report. And don't worry about the graphics. To be quick, you can just look at these numbers. These are in meters of sea level rise. In the year 2100, under a low emissions RCP 2.6 scenario, the central estimate, the best guess as of the SROC report's publication, was about 43 centimeters of sea level rise. And you can see that in a high emissions case, it doubles. Now, if we have a longer term perspective out in the year 2300, there isn't much of a change between 2100 and 2300 in the low emission scenario. That's great news. But in a high emission scenario, like an RCP 8.5, there's a huge potential for sea level rise. And you can see that at the high end, this is the top of the likely range of the estimates, it's 5 times greater in the high emissions than the low emissions. So clearly, for sea level rise, mitigation is of critical importance, important message. You can see that in the long term, there's a huge uncertainty in the magnitude of sea level rise, and that, as you'll see, is driven by Antarctica. The Antarctic ice sheet is huge. It contains enough ice to be the equivalent of 57 meters of sea level rise. And just, if those of you who don't work on this, here's the United States superimposed on the Antarctic continent for scale. We're talking about kilometers of ice cover on this massive continent. Now, Antarctica is fringed by floating extensions of the ice sheet flowing out into the sea, and we call these ice shelves. So snow falls in the interior, the snow turns to ice, the ice is heavy, it deforms and flows downhill toward the sea under its own weight and extends into these floating ice shelves. The floating ice shelves are critical because if they bump into something on the seafloor, they provide some structural support that slows the flow of the ice from the interior out into the sea. So what we're worried about and what we are observing is that these ice shelves today in a warming ocean are beginning to thin and they're losing their strength, in this buttressing support that's holding back the flow of ice from the ice sheet out into the sea is weakening. In places where that is happening, the ice is flowing faster into the ocean. So the latest generation of models that actually account for these very complex physics, and this is a great challenge in modeling this system, these are what I wanted to show today, is that this is a perspective looking from the year 2000 to the year 2100, so the 21st century. And just if we look at these red lines, this is the rate of sea level rise contributed by Antarctica in a scenario where we limit global mean warming to plus 1.5 degrees C, like a Paris Agreement aspiration. And what we find is that the rate of sea level rise really doesn't change much throughout the 21st century relative to today, if we're able to maintain warming at 1.5. In a +2°C warming scenario, there's a little bit of an uptick late in the 21st century in the loss of ice on Antarctica, but there's no real stepwise difference. This is great news. When we just allow +3°, so essentially following something close to the current NDCs, you can see that there's a big difference in the red curve. There's a big jump in the rate of ice loss on Antarctica, and it's because we're beginning to lose those critical ice shelves that fringe and apron around the continent. We're getting, for example, 15 centimeters of sea level rise just from the Antarctic ice sheet in the year 2100, which is about at a rate of sea level rise that is about 10 times faster than the rate of sea level rise coming from Antarctica today. So we've crossed a threshold somewhere between +2 and +3°. What's happening is, here's a model simulation of the Antarctic ice sheet as it looks basically today. And I want you to just keep your eye on this sector of Antarctica. This is the West Antarctica, the West Antarctic ice sheet. And there's a very wide, very deep glacier here called the Thwaites Glacier that drains much of the interior of the West Antarctic ice sheet. These light blue colors that are seaward of these black lines, this is where the ice sheet ends and the ice shelves begin. So this is floating ice, this is floating ice, this is floating ice. These are the ice shelves, and you can see them fringing around much of the continent. So here's 1950. We're going to follow a +3°C scenario following the current NDCs roughly. And +3° in the year 2100 for the NDCs is conservative, by the way. Most recent estimates now are as high as +3.5. Here's 2100. And what you can see is that we're beginning to thin these ice shelves around the continent. Some have been lost entirely. We've got our 15 centimeters of sea level rise from Antarctica. And now when we go to 2300, very different picture. And we see that the Thwaites Glacier has basically eroded into much of West Antarctica. We would be potentially talking about 1 to 2 meters of sea level rise coming out of just the Antarctic ice sheet. So this would be additional onto all the other things that cause sea level rise: thermal expansion, glaciers, Greenland ice sheet, and so forth. Okay, so then to sort of wrap up what we've been able to test and look at, and this is an important message, is that once something like this begins to happen, and for example, the Thwaites Glacier begins to collapse and West Antarctica is retreating, can we stop it? And so what we do is we start down the path following the NDCs, and then we imagine that we can remove CO2 through carbon dioxide reduction. Somehow magically we'll have developed the technology to do this. And so we follow the NDCs, and then we say in the year 2050, for example, we start very rapid CO2 drawdown. What we find is that if we follow the NDCs, we trigger rapid ice loss, even if carbon dioxide reduction were to commence as soon as about 2060 to 2070. So once these processes begin, we lose those buttressing ice shelves. There's really no turning back, because the ice shelves can only regrow if the oceans are cold enough again to allow them to regrow. And once you put a lot of heat into the ocean doesn't cool down again quickly. So there's an important message here. Delayed mitigation in the very near term has a major effect on sea level rise for centuries into the future. Okay, then lastly, the numbers, for example, in the NDC scenario, +3°C, 15 centimeters from Antarctica might not sound catastrophic. If we have a little bit of a longer term perspective, it's really the 22nd century after the year 2100 that the ice sheet in Antarctica really wakes up. In the high emission scenario, these are examples. In the year 2200, we would potentially be looking at 5 meters of sea level coming from Antarctica. In the year 2300, 10 meters of sea level rise coming from the Antarctic ice sheet. And if we think about what that would do, for example, to some areas in southern Sweden, everything we see in blue here is inundation of land. This is not storm surge, flood. This is inundation with 5 meters of sea level rise, and this is 10 meters. in a high emission scenario. So to conclude, the most recent work, and this is something that just appeared in Nature just about a month ago, if we let global temperatures rise above 2 degrees C, we're significantly increasing the risk of triggering rapid ice loss from Antarctica, which for the Antarctic ice sheet would be irreversible and unstoppable. So the current NDCs and NDCs from this modeling perspective are not good enough. Overshooting the aspirations of any more than plus 2 degrees, even for just a few decades. So this is the overshoot point. We cannot have an overshoot, because if just a few decades go by above plus 2 degrees, we're worried about triggering these instabilities again that would be irreversible. So overshooting is not an option. And there's a lot of uncertainty in these numbers. Exactly where that threshold is would be much better off if we can stay closer to plus 1.5. And then lastly, the higher emission scenarios, if we were to go anything above the NDCs, for example, we would be talking about sort of catastrophic potential rates of sea level rise coming from the Antarctic ice sheet. And I'll conclude there.